Make a rough estimate of how far food coloring will diffuse through water in 1 minute. Okay, so we know that the change in time is 1 minute, and there is an example. He does an example to show you how to approximate these things in the book. We can follow along the same way, and for this problem we have to use the Fick's law of diffusion. Fick's law of diffusion. And what this says, Fick's law of diffusion, it's saying that J, which is the particle flux, okay, it's a vector particle flux, that's equal to minus d, which is the diffusion coefficient, times dn over dx. N stands for the particle concentration and x is the distance along the x-axis. So dn over dx will be the change in the particle concentration as we move along one dimension. Okay, now that would make sense, of course, because the more it is what you'd expect it to be, because as the number of molecules, or as the concentration of the particle increases along an infinitesimal distance, the flux of the particle will tend to drive it away from that location even more, times some constant which they call which is d, diffusion of coefficient. And the minus sign is there because if dn over dx is positive, right, meaning as you go to the right on the x-axis there's more particles available, clearly if there's more particles available, particles will tend to go towards where there's less particles available, so they will tend to go backwards in the negative x direction, and that's where that negative minus sign comes in. Okay, now if the food coloring is let's just assume it's spread evenly through 1/2 of some volume in space, and let's say that this volume in space has a width of delta x and an area of A. So we know that volume is area times delta x. That's where it's gonna spread. That's where the coloring will spread. So then if we apply this into Fick's law of diffusion, so we know that again J is being the flux, and what that means, this is the net number that cross it, okay, cross any surface. It's the net number that crosses any surface per unit area per unit time. So this is the net number of particles crossing a surface per unit area per unit time, delta t. So in other words, I could replace J with the net number of particles crossing a unit area in some delta t. In this case it's 1 minute, and that has to equal, on the right hand side we have d. So I'm just gonna use absolute values since I'm just finding how far. So this is gonna be d times the number of particles. We said this is the particle concentration, this is how many particles I have per volume, divided by dx, which would say it's delta x. Okay, so now we have same n on both sides, right? So that means we want a substantial fraction of the molecules, a big amount, to cross from one side of the region to the other. So I could count, since A is the same here, right? Now V is A delta X. So this is V is just A delta X, and I already have a delta x squared, so this becomes delta x squared. Okay, so I could cancel the a's and the n's, and by the way, I'm using here changes, delta x instead of differentials, just because this is an approximation. Okay, so this is gonna be delta x equal d times delta t, and then square root it. And so if we plug in the numbers, right, now what's the in the book he gives the rate, the diffusion coefficient. He says it's for food molecules in water, diffusion coefficients are near 9 times 10 to the minus 9. That's for 1 second. We have, yeah, 5 times 10 to the minus 10. Let's see if we have the, yeah, it's on page 48. For sugar it's 10 to the minus 9, so this will be 10 to the minus 9 meter square over second times a minute is 60 seconds. And so we get for delta x the seconds cancel. We get 2.45, 1 2 3 4 2.45 times 10 to the minus 4 meters. So this is how far it will travel in 1 minute. This does it.